Hey guys, so before we jump into accumulation functions and what they are, we need to review some really important vocabulary from last semester. So f of x has a critical point when the first derivative, so f prime of x, is equal to 0 or f prime of x does not exist. So we spent a lot of time analyzing graphs of f and functions of f and then their derivatives and looking at all of these different things. So critical points are when the first derivative is 0 or the first derivative is undefined. F of x is increasing when the first derivative, f prime of x, is greater than or equal to 0. So in other words, f prime is increasing anytime it has a positive slope. So another way we can say is increasing is we could say that f has a positive slope. When f prime of x is greater than or equal to 0. F of x is decreasing when the first derivative, so f prime of x, is less than or equal to 0. So, in other words, f has a negative slope. When f prime is less than 0, and we know that a negative slope means that the function is decreasing. All right? Then let's talk about the points of inflection. So f of x has a point of inflection when the second derivative equals 0 or is undefined, so it does not exist, and the second derivative changes sign. So we know points of inflection tell us when the concavity changes. So if the function changes from concave up to concave down, or concave down to concave up, then we know it's a point of inflection. So it's really important to make sure we have both of those pieces. Either that the second derivative is 0 or does not exist, and that the second derivative changes sign. F of x is concave up when the second derivative, f double prime, is greater than 0. And we know that when it is concave up, it looks like a cup. So that's why I almost wrote the word cup, my bad. And then we know that f of x is concave down when the second derivative, f double prime, is less than 0. For a function to be concave down, we know that it looks like a frown. All right, when we looked at minimum and maximum, we had two different ways we could kind of think about finding the min or the max. So, f of x has a maximum when we kind of have two options here. So option 1 is that f prime changes from positive to negative. So in other words, the function changes from increasing to decreasing, and that causes us to have a maximum on our function. The second way that we could have a maximum would be if we know that the first derivative is equal to 0, and we know that the second derivative, so f double prime, is less than 0. We know that if the second derivative is less than 0, the function is concave down. And if we know that the first derivative is 0, there's a horizontal tangent, which means we must be at the top, we must be at a peak, and that creates a maximum. We've got similar things for finding a minimum. So f of x has a minimum when the first derivative, so f prime, changes from negative to positive. So in other words, our function went from decreasing to increasing. That causes us to have a minimum value. Or we could look at the first derivative equals 0, and the second derivative, f double prime, is greater than 0. If the second derivative is greater than 0, our function is concave up. And then since the first derivative is 0, we're looking at that horizontal tangent. So again, we're down at the bottom now. We have a minimum value. To find an absolute maximum or an absolute minimum, we've got really the same process here. All right, so f of x could have an absolute max. At x values where f prime of x equals 0, or at endpoints. So it's always very careful. We always have to be very careful. It's important to make sure that we double check the endpoints of a function as well. Then once we have our values where f prime of x equals 0 and we've got the endpoints, we need to make an options chart. Options chart. Wow, I cannot talk. Make an options chart. Sorry about that. Then for an absolute minimum, f of x could have an absolute min when f prime is 0 or at the endpoints. And again, we're going to make that options chart. So just to remind you, our options chart has x and y, and we will substitute the values where f prime is 0 and the endpoints into the function, and then we'll just pick the absolutely highest for the absolute max, and then the absolute minimum is obviously the smallest. Okay? So we had to review that really important vocabulary from last semester because we're going to need it for these coming problems. The next thing we have to review really fast is the fundamental theorem of calculus. This is what we just did in our last chapter. So we're going to take the derivative of these functions here, and hopefully you can recognize that this is that fundamental theorem. So dy dx is going to equal the sine of x squared times 1. So I took my upper bound and substituted it into the function, and I multiply by the derivative. And then I subtract, and I plug in my lower bound, and multiply by the derivative of my lower bound. So the derivative of 4 is 0. That second piece cancels out, so I get that dy dx is equal to the sine of x squared. For number 2, dy dx, I substitute my upper bound into my function. So it's the sine of 3x squared plus 7x squared times the derivative of my upper bound, which is 6x plus 7. And then hopefully you guys can see that that second piece is going to cancel out because the derivative of 4 is 0. So it ends up canceling out. And I'm just going to go ahead and rewrite my answer in a nicer way. So 6x plus 7 times the sine of 3x squared plus 7x squared. That's my dy dx. So this fundamental theorem of calculus and these vocabulary words, we need them in order to understand the problems that are going to come at us in this section. So let's go ahead and take a look then at what an accumulation function actually is. So believe it or not, we have been dealing with accumulation functions, I just haven't necessarily been calling them that. So an accumulation function is any function that's defined as the integral of a different function. So for example, if I told you that g of x is equal to the integral of f of t dt, and I put a number for my lower bound and x for my upper bound, that's generally what this is going to look like. Then what I'm saying is that g of x is my accumulation function. Sorry about that. So let's take a look at what this is going to look like in an actual question. So f is a function defined on the closed interval from 0 to 7. The graph of f, consisting of 4 line segments, is shown below. So it's really important to note that we're given the graph of f and that it's 4 separate line segments. So even though it doesn't look like it, these are separate lines right here. And let g be this function given by g of x equals the integral from 2 to x of f of t dt. So g of x is our accumulation function. Let's look at what some of these things are that they're going to ask us about. So first thing they ask us for is g of 3. So all we're going to do for this is substitute that in. So the integral from 2 to 3 of f of t dt. And hopefully you should be able to look at this and you should recognize that this integral really just means find the area under the curve. This is what we've been doing since we first started talking about integrals. So when we look from 2 to 3, we can see that that's a trapezoid. So the height of my trapezoid is 1, so I'm going to have 1/2. The first base is 4, and my second base is 2, so 4 plus 2. So I have half of 6, which is 3. So g of 3 is really just 3. The next question asks us to find g prime of 3. Well, before I find g prime of 3, I want to talk about g prime of x. And I want to actually find the derivative of this function first. So the derivative is going to be d dx of this integral, 2 to x of f of t dt. Now hopefully this also looks familiar. This right here is what we just reviewed. This is the fundamental theorem of calculus. So we can really easily take the derivative. It's the derivative of an integral, which means this is actually going to end up just being f of x. Because we know that when we plug in that 2 and take the derivative of 2 is 0, so the second piece ends up canceling out. Which means it's really important to note, we just said that g prime of x is equal to f of x. So this graph of f is really also the graph of g prime. So I'm going to just kind of make a note of that. It's going to be important as we keep moving forward. So that means then if I want g prime of 3, that's really f of 3, which is just what's the function value at 3. So that's equal to 2. Let's see, the next thing they're asking for is g double prime of 3. So kind of like up here where all I did was focus on what's g prime of x, let's find g double prime of x first also. So the second derivative, g double prime, really means I'm going to take the first derivative of x. So g double prime of x equals f prime of x. So if I want the second derivative, g double prime of 3, that's going to mean I want f prime of 3. And we know that f prime of 3 really means the slope of f of x at x equals 3. So if I go to my graph here, this is the graph of f. I want the slope at 3. We know this is a line segment, so we can just use regular old slope. So let's see, we're going down 2 and over 1. This is a slope then of -2. So those were all pretty basic questions that kind of just came from the graph. Now we're going to look closer at what other kinds of questions they could be asking us. This is where the vocabulary is going to come in. So find the critical points of G, then identify where G is increasing and decreasing. We know that to find the critical points, it needs to be where the first derivative, G prime, is equal to 0 or does not exist. And we know that for G to be increasing, we're looking for the first derivative to be positive. And for G to be decreasing, we're looking for the first derivative to be negative. So let's look at each of these separately then. Let's do the critical points first. So to find critical points, we need the first derivative to equal 0. So G prime of x. But we said that G prime of x is the same as f of x, which means I want G prime, which is the same as f, to equal 0. So really all I'm looking for are the x-intercepts of this graph. So 0, 4, and 6 would be my critical values. X equals 0, 4, and 6. Those are my critical points. And then I'm going to look for where G of x is increasing. We said that that's where G prime, which is the same as f, is greater than or equal to 0. For f of x to be greater than or equal to 0, it means we want to look at this graph and see where f of x is above the x-axis. So we know that that's going to be from 0 to 4, and then again from 6 to 7. And then lastly, we're going to look at where G of x is decreasing. So we need to know where G prime, or where f of x, is less than or equal to 0. So where is f of x below the x-axis? That's going to be from 4 to 6. And there we go. All right, moving on. So you'll notice here that this next part, we're still using the same graph. All right, we're looking at G of x and f of x, and we've got the same graph and the same accumulation function. So what I want to do really quickly is I want to just make a note that we had said f is the same as G prime. And also we made a note that G double prime is the same as f prime of x. So those are going to be important just as we continue. Those are just notes from the last page. All right, so find the x-coordinates of the points of inflection. So we know that points of inflection are where the second derivative equals 0 or does not exist, and the second derivative changes sign. Then we're looking for where G of x is concave up and concave down. So we're going to be looking at where G prime is positive and G prime is negative. So let's find our possible points of inflection. So again, we're looking for where G prime is 0 or does not exist. So just as a reminder, for G prime to be does not exist, we're looking for corners, cusps, or vertical tangents. And then for it to be 0, we're looking for horizontal tangents. So let's see, we have possible points of inflection at 2 and 5 for sure, but it's important to note that we also have one at 4. Because at 4, those are two separate lines, so there's kind of this corner cusp thing going on there. So the second part, though, for the points of inflection is that we need the second derivative to change sign. So when we look at, and I'm sorry, that shouldn't be 0, that should be 2. Sorry, I hope you caught that before I did. So we have this corner up here at 2, the corner down here at 5, and then this cusp corner thing at 4. So the actual points of inflection, sorry guys, this is my 4th time making the video. I've made so many mistakes I can't even, and I don't want to make it again, so I'm sorry. We need the second derivative to change sign. And we know that the second derivative is really the same as f prime of x. So we're going to be looking at where does the slope of f change here. So we can see that at 2, f prime changes from positive to negative. So we know that x equals 2 is definitely a point of inflection. At x equals 4, the slope of f is negative and then negative again. So that one does not change sign. And then at 5, the slope is negative and changes to positive. So that one is a point of inflection. Okay, so there we go. Now let's look at where the function is concave up, and hopefully I don't make any more mistakes from here. Sorry guys. So for the function to be concave up, we need the second derivative of g, so g prime of x, which is the same as f prime of x, to be greater than 0, because we want the second derivative to be greater than 0. So concave up. So what we're really saying here is that we want f to have a positive slope. So let's see, f has a positive slope from 0 to 2. Oops, 0 to 2. And then it has a positive slope from 5 to 7. So that is where the function is concave up. And then let's look at the function being concave down. So we want the second derivative of g, which is the same as f prime of x, to be less than 0. So in other words, we're looking for where does f have a negative slope. So f has a negative slope from 2 to 4, and then again from 4 to 5. Okay, I know it's getting long. We've got 2 more to go. I'm sorry. Identify the x-coordinates of the absolute maximum and absolute minimum of g of x. So we know that absolute maxes and mins occur at the critical values. So the first thing we're going to do is we're going to pull the critical values that we found on the last page. So we said those occur at 0, 4, and 6. And what we're going to do is we're going to make our options table that I was talking about at the beginning of the video. So we've got x and we've got g of x. And we need to put our endpoints and our critical values in there. So we're going to have 0, we're going to have 4, we're going to have 6, and we're going to have 7. Notice I kind of spaced them out. That's because we're going to have to actually substitute these in to the function that we have above. So g of 0 means take 0 and plug it in here. So we're going to do the integral from 2 to 0 of f of t dt. Well, I'm going to flip the bounds on that, so I'm going to make it negative 0 to 2 of f of t dt. And all that means then is I need the area from 0 to 2. So that's a simple triangle. So I'm going to leave my negative sign, and it's 1/2, the base is 2, and the height is 4. So I get an area of negative 4. And then to plug in 4, I'm going to do the integral from 2 to 4 of f of t dt. So again, that's just another triangle from 2 to 4. So it's 1/2, the base is 2, and the height is 4. So I get an answer of 4. And then to do the integral from 2 to 6 of f of t dt, I'm actually going to break up this integral because I just found the integral from 2 to 4 of f of t dt. And now I can just do 4 to 6. So let's see, the integral from 2 to 4 was 4. So now I need to add whatever the integral is from 4 to 6. So from 4 to 6, it's this triangle that's underneath the x-axis. So it's actually going to be a negative 1/2. The base is 2 and the height is 1. So I have 4 minus 1, which becomes 3. And then one more to go. But similarly, since I'm doing the integral from 2 to 7 of f of t dt, I'm actually going to break that up as the integral from 2 to 6, because I just found that, plus the integral from 6 to 7 of f of t dt. So let's see, I have 3, and now I just need to do the integral from 6 to 7. So 6 to 7 is just a little triangle with a base of 1 and a height of 1. So I get 3.5. And now what I need to do is I actually want the absolute maximum and the absolute minimum. So the absolute maximum is going to be 4, and it occurs at x equals 4. So I'm going to say that G has an absolute max of 4 at x equals 4. And then I need to find the absolute minimum, so let's go ahead and do that. The lowest that this is negative 4, and that occurs at 0. So g of x has an absolute min of negative 4 at x equals 0. Okay, I know that this question is a lot of work, all right? When you get this on an FRQ, this is going to be worth a bulk of the points on that actual question. So you have to know how to do this. It's a lot of work, all right? It's a lot of plugging in and a lot of really thinking, but if you know the vocabulary, you can do it. All right, we have one more. I'm sorry. Please bear with me. Find the average rate of change of g on the interval from 0 to 3. So hopefully you guys can look at this and immediately know that average rate of change really just means find the slope. So the slope of g from 0 to 3 really just means g of 3 minus g of 0 all over 3 minus 0. We found g of 3 on the last page, so g of 3 is actually 3. And then we just found g of 0 up here, it's negative 4. And then over 3, so we really get that the average rate of change is going to be 7 over 3. Alright, again, I know it was a little bit, well, a lot of it, of a longer video, and there's a lot in there, and I know I screwed up a couple of times, my bad. But hopefully you got it all. We're going to do a lot of practice, but these are going to be super important as we go forward. So if you have questions, you have to ask. Alright, I'll see you guys later. Bye!